Hello and welcome to Chapter 3. So let's go over the learning objectives for this week. So we're going to talk about surveillance in epidemiology. Your book talks a lot about surveillance. We're going to talk about what is incidence rates, and specifically we're going to talk about different types of incidence rate, cumulative incidence rate, incidence density, and so on and so forth. I'm going to show you how to calculate incidence rates, and specifically, I want you to pay attention as we're going to see what goes in the numerator and what goes in the denominator. And finally, we're going to try to illustrate why incidence data are necessary for measuring risk. Okay, we're going to talk more about risk soon. So surveillance. Surveillance is one of the primary roles of public health. The purpose of surveillance is to capture any changes in the level of risk factors. Surveillance also used to monitor the number of people who completed their vaccinations. As you can imagine, if the number of expected people that need to be vaccinated drops, that means that the local public health department needs to be on alert of disease outbreaks. So let's now talk about types of surveillance. Passive surveillance utilizes existing data. In our days, there are several online sources that we can use to retrieve epidemiologic data. Some of those online resources include Google, CDC, Medline, WOSIS or World Health Organization Statistical Information Systems, and any websites from organizations and publications related to epidemiology, such as APHA and many others. Decision makers utilize such resources as guides for developing and implementing programs for disease control and prevention. As you can imagine, a major limitation to obtaining data from passive surveillance is underreporting and lack of standardization. Different states may have different way of recording information, and busy doctors and nurses may fail to report all cases. Active surveillance, on the other hand, takes place in the present. Project staff make periodic field visits to healthcare facilities and identify and record new cases of disease. Active surveillance is expensive and very time consuming, since it may require agents to interview doctors, nurses, and patients and review medical records. Active surveillance is more accurate since the people employed to carry out the surveillance are employed for that reason alone, so they are less likely to underreport. This figure is from your text, and it shows how individuals move from a healthy stage to the various levels of disease. What I want you to think here is that going from a healthy stage to getting admitted to a hospital takes time. First of all, the person needs to become infected or sick, and at the very beginning he or she will be unaware. Infectious diseases show fairly quickly, while chronic diseases take years to show symptoms serious enough for someone to take action. Eventually, the individuals may have to spend time in the hospital, where the outcome can vary from getting well to maintaining health through medicine or dying. Here again, you can observe the progression of disease in a population, but do notice that death can occur in any of these rectangles. So why is it important to keep monitoring the ratio between sick and the total population? What do you think? We need to keep monitoring in order to prepare accordingly. We cannot manufacture vaccines overnight, and we cannot create successful interventions if the disease gets out of control. So how do we measure the relative incidence of a disease? We usually calculate incident rates or attack rates or prevalence. Let's start with the incidence. The critical element in incident rates is new cases of disease. We only try to capture the people who just got sick and not everyone who is sick from the same disease. Time is important here, since we are measuring individuals who go from a non-disease state to a disease stage. Thus, the incidence rate is a measure of risk. This is a very important slide since it gives you the key concept that we need to be met in order to include individuals to our calculation for incidence rates. We only count in the numerator new cases of disease. The denominator, which is the population at risk, cannot include persons with the disease, and of course time is required for individuals to transition from one stage to another. Two common measures of incidence. The cumulative incidence rate, also known as incidence rate, especially for public health surveillance, consists of the number of persons who newly experienced the disease or the studied outcome during a specified period of time divided by the average total population at risk. So if you're at risk, that means you do not have the disease. This calculation assumes all persons in the denominator contribute an equal amount of time in the measure. It is usually presented with an upper and lower bound. Incident density rate, also known as incident rate as well, or person time rate, is the number of persons who newly experience the outcome during a specified period of time divided by the sum of the time that each member of the population is at risk. This is also presented with upper and lower bounds. This is the equation for cumulative incidence rate. The numerator consists of only the new cases of disease during a specified period of time, and the denominator is the number of people who are at risk for developing the disease but do not have the disease during that time. You always multiply with a base. The number that you can see right here, okay, it's usually 1,000 or 100,000, okay, or any figure for that matter. Depending how large a population is, we may use a different base to simplify calculations. Keep in mind that I will always provide you with a base in all your word problems, and you only need to make sure you specify so in your answer. Another important part of the cumulative incidence is the concept of time. Incidence rates can use two types of denominators. Number one would be people who are at risk are observed over a defined period of time. And number two would be when all people are not observed for the full time period, then we use person time, okay, or units of time for, and then we add that up. And I'm going to show you exactly what I mean on subsequent slides. You're probably too young to remember the Chernobyl explosion in Russia, but it was one of the worst disasters in history since it had severe health effects on millions, and not only in Russia. The above graph depicts the incidence rate of childhood thyroid cancer in Belarus, Ukraine, and Russia the years following the explosion. Needless to say that this graph does not capture all the nations affected, since countries such as Bulgaria or even my country, Greece, which are quite far from Russia, had an elevated number of childhood cancer. Notice how low the incidence rate was all the way up to 1988, right here, and how it skyrocketed in the 1990s, right? So it just completely went straight up. Here's an example of how to solve cumulative incidence. You will see similar problems to this one in your homework and exams. All right, so here we're talking about sudden death syndrome during the first year of life. You can see that your total population at risk is 1,000 live births. You have 10 cases of SEED, right? And based on the equation that I gave you, right, you would take your new cases of disease, the 10, and you're gonna divide it with your live births, right? Because these are people who are at risk for SEEDs, right? Not all births, because not all births are live. So you would only calculate live births, right? And then you would multiply that with a base, okay? So all live births are at risk. Person time is a very important concept in epidemiology. Ideally, everyone should be followed for the entire time for a specified period of time. Imagine you design a study and you follow people over time. You decided to follow all your participants for 5 years to see who develops a disease. Unfortunately, not everyone will be able to remain in your study the entire time. People move, die, or simply don't want to be part of your study anymore. Thus, you will need to capture those changes in your denominator. When different people are observed for a different amount of time, we calculate an incidence rate, also known as incidence density, in which the denominator consists of the sum of the units of time each individual was at risk and was observed. For example, if you look at the above figure, the study is supposed to follow people over 5 years. So right here you have years 1, 2, 3, 4, 5, and you have 5 participants. Participant number 1, 2, 3, 4, 5. And you're supposed to follow all 5 participants for 5 years. That means 5 person years for the first person, plus 5 person years for the second person, another 5 years for the third one, for the fourth, and the fifth. Thus, the total is going to be 25 person years. That would be your denominator if nobody left your study, right? In this figure, though, as you observe that everyone started at the same time, but not all were observed for the same amount of years. The first person was observed the entire 5 years. The second person observed only for 1 year. The X here indicates disease, so the person here became sick. So since it became sick, he's no longer at risk, right? The third person was observed for 2 years. The fourth person was observed for the entire time of the study. And then the fifth person was observed for 4 years. So now we would calculate, we would add those units, so 5 plus 1 plus 2 plus 5 plus 4, that would equal 17 person years. This is the incidence density rate calculation. EPI problems, as you will see from your homework, are very wordy, and you will need to read carefully and identify the correct information in order to solve. Pay attention and ask yourself if the problem gives you new cases of disease or existing cases of disease, since that will make a huge difference. Also pay attention to the base. I will always give you a base and you need to include it both in your calculations and in your final answer. To calculate the incidence rate, we divide the new cases of disease with the person years. In the figure above, the X represents new cases of disease at that time. So we have 3 new cases of disease, and the total person years is 17 as we calculated previously. Thus, the incidence density or incidence rate would be 3 over 17 times 100. That is the base that we're using. That means you have 17.64 person years, okay? This is another example that I'm giving you. Please try to solve this on your own before you look at the solution in your PowerPoint. For the sake of saving time in my recordings, I will not explain every single example that I include in your PowerPoint. So read it on your own, and if you see that you're struggling, come and see me. This is again the answer here. Try not to look at it. Now, I do want to call your attention on how you're going to state your answer. Epidemiologists are very specific on how they state information. Pay attention to all the slides that I tell you how to properly state your answers depending what you're calculating. So, based on the type of calculation you are performing, you will be stating your results differently. In fact, you will see different statements in your exam, and you will have to select the correct one for the example given. In this particular case, we were calculating incidence rates, and the full answer would be for 2011, the incidence rate of pink eye in Fullerton School District was 231.5 cases of pink eye per 1,000 students. Okay, so 1,000 students here, that would be your base essentially. Again, this would be the results of solving your incidence rate. I assume you all took statistics since it is a prerequisite for this course, so you should all be familiar with the concept of a sample versus a population. When it comes to identifying new cases of disease, the ideal way would be to monitor the entire population. Of course, this is not always feasible, as we rely on quality samples to infer about populations. Now you may be wondering what to do with people who have the disease already. Do we calculate them, and is it important to know the proportion of people who are diseased? We do, and it's very important. Simply the calculation that includes existing cases of disease is called prevalence, which is coming up in the lecture after this one. Incidence rates are very important, but as we said previously, it relies on quality surveillance. Furthermore, the onset of certain diseases can be very long, so it's very hard to identify when the disease really starts. Think of arthritis or Alzheimer's disease or even cardiovascular disease. Chronic diseases take time to develop, so knowing the exact start time may be impossible. Why do we need and where do we need incidence rates? Mostly for planning or etiologic research, looking for causes. For example, if we see that by October an increased number of people is admitted to the hospital with flu symptoms, we may start to anticipate a very heavy flu season. So we may want to plan and increase the number of vaccines that we're going to produce and maybe invest more to inform the public. So this is it for this lecture. Notice that in your PowerPoint you have extra examples and their solutions as I previously stated. So I suggest you print them and study along with reading with your text. Have a good